Take a slow, comfortable breath and allow your shoulders to relax. Tonight, you are invited on a calm and unhurried journey through our solar system, a vast, quiet neighborhood of planets, moons, and gentle cosmic rhythms that have existed for billions of years. Far above the noise of daily life, beyond cities, economies, and schedules, the planets continue their steady paths around the sun, unchanged by human worries. This peaceful consistency is part of what makes space such a comforting place to explore before sleep. If this is your first time here, welcome. And if you've returned for another restful night, it's wonderful to have you back. This experience is designed to be slow, soothing, and curiosity-driven. There is nothing you need to remember, nothing you need to do, and no pressure to stay awake. Simply let the facts drift past like distant stars seen through a quiet window. If you find that you enjoy calm learning like this, blending education, nature, and gentle storytelling, you may choose to like the video or subscribe to the channel. And if you feel comfortable, you're invited to leave a comment sharing your country, your city, and the time you're listening right now. People from all over the world listen together, quietly connected by curiosity and calm. Now, let's begin our slow tour of the solar system. Our solar system formed about 4.6 billion years ago from a vast cloud of gas and dust called a solar nebula. Over immense stretches of time, gravity gently pulled material together, forming the sun at the center and the planets from leftover matter. This process was not sudden or violent in the way we often imagine. Instead, it unfolded gradually, like dust settling in still air, guided by gravity's patient pull. At the center of everything is the sun, a nearly perfect sphere of hot plasma that accounts for more than 99% of the solar system's total mass. Its steady energy supports life on Earth, influences planetary climates, and shapes the movement of every planet, moon, asteroid, and comet. Even from millions of kilometers away, the sun's gravity acts as a quiet anchor, holding everything in balance. The planets orbit the sun in slightly flattened paths called ellipses. No planet travels in a perfect circle, though some come very close. These orbital paths are stable over long periods, allowing planets to return again and again to familiar positions, much like a calm routine repeated across billions of years. Our solar system is often divided into two main regions: the inner planets and the outer planets. The inner planets, Mercury, Venus, Earth, and Mars, are rocky worlds with solid surfaces. They formed closer to the sun, where lighter gases were pushed away by solar energy. Farther out, beyond the asteroid belt, the outer planets, Jupiter, Saturn, Uranus, and Neptune, are much larger and composed mostly of gas and ice. Mercury, the closest planet to the sun, is also the smallest. Its surface is covered in craters, much like Earth's moon, preserving a record of ancient impacts. Because Mercury has almost no atmosphere, temperatures vary dramatically. Daytime can be intensely hot, while nighttime can be bitterly cold. Despite being closest to the sun, Mercury is not the hottest planet, a fact that gently surprises many listeners. That distinction belongs to Venus, a planet often called Earth's twin because of its similar size. Yet Venus is wrapped in thick clouds of carbon dioxide that trap heat through an intense greenhouse effect. Its surface temperature is hot enough to melt lead, and its skies glow with reflected sunlight. Venus rotates very slowly and in the opposite direction of most planets, meaning its days are longer than its years. A reminder that planetary time does not follow human intuition. Earth, our home, occupies a narrow region known as the habitable zone, where liquid water can exist on the surface. Oceans cover more than 70% of the planet, influencing climate, weather, and the development of life. From space, Earth appears as a calm blue sphere, its clouds drifting slowly, its continents quietly turning beneath them. The balance of atmosphere, magnetic field, and distance from the sun allows life to flourish in extraordinary diversity. Mars, often called the red planet, owes its color to iron oxide, essentially rust, on its surface. Once, long ago, Mars had flowing water, lakes, and perhaps even shallow seas. Today, its surface is cold and dry, but evidence of ancient rivers remains etched into its landscape. Robotic explorers continue to study Mars, searching for clues about its past and the broader story of planetary evolution. Between Mars and Jupiter lies the asteroid belt, a region filled with rocky remnants left over from the early solar system. These objects range from tiny pebbles to dwarf planet-sized bodies. Contrary to popular imagination, the asteroid belt is mostly empty space, with vast distances between objects. It serves as a quiet boundary between the inner and outer solar system. Jupiter, the largest planet, is a gas giant with a mass more than twice that of all other planets combined. Its powerful gravity shapes the solar system, influencing asteroid paths and helping protect inner planets from frequent impacts. Jupiter's atmosphere is a tapestry of swirling clouds, storms and bands, including the Great Red Spot, a storm larger than Earth that has raged for centuries. Saturn is famous for its stunning ring system, composed of ice and rock fragments orbiting in delicate balance. Though the rings appear solid from afar, they are made of countless individual pieces, each following its own path. Saturn's low density means it could theoretically float in a sufficiently large ocean, a gentle reminder that appearances can be misleading in planetary science. Uranus and Neptune are known as ice giants, composed of heavier elements such as water, ammonia, and methane. Uranus is tilted dramatically on its side, resulting in extreme seasons that last decades. Neptune, the most distant planet, is known for its deep blue color and powerful winds, some of the fastest observed in the solar system. Beyond the planets lies the Kuiper Belt, a distant region filled with icy bodies, including Pluto, even farther out. The Oort cloud may surround the solar system, a vast and quiet reservoir of comets, extending halfway to the nearest stars. As we continue, we'll explore each planet more deeply, moving slowly, calmly, and thoughtfully through their unique stories. There is no rush. The solar system has waited billions of years, and it will continue to wait quietly as you rest. As you continue listening, imagine drifting closer to the center of our solar system, toward a presence that feels both powerful and calm. The sun does not rush. It does not flicker or hurry. For billions of years, it has shone steadily, shaping every planet, moon, and grain of dust that moves within its reach. Tonight, we gently explore this quiet heart of our planetary neighborhood. The Sun is a star, but it is the only one close enough for us to study in intimate detail. It formed around 4.6 billion years ago, at the same time as the rest of the solar system, when gravity slowly pulled gas and dust into a dense, glowing sphere. This process took millions of years, unfolding at a pace that feels almost meditative when compared to human timescales. Composed mostly of hydrogen and helium, the Sun generates energy through nuclear fusion in its core. In this process, hydrogen atoms fuse together to form helium, releasing enormous amounts of energy. This energy travels outward, layer by layer, taking thousands of years to reach the Sun's surface. Only then does it begin its 8-minute journey across space to reach Earth. Even sunlight, which feels instant to us, carries the memory of a very long voyage. The surface of the Sun, called the photosphere, has a temperature of about 5,500 degrees Celsius. Beneath it lies the convection zone, where hot plasma rises and cooler plasma sinks in slow, rolling motions. These movements create the subtle, grainy texture seen in high-resolution images of the Sun. Above the photosphere, the Sun's atmosphere extends outward in layers, including the chromosphere and the corona, which glows softly during solar eclipses. The corona is much hotter than the Sun's surface, reaching temperatures of over 1 million degrees Celsius. This surprising fact continues to intrigue scientists and reminds us that even familiar objects can hold quiet mysteries. The corona gradually blends into the solar wind, a gentle but continuous stream of charged particles flowing outward through the solar system. This solar wind interacts with planets in different ways. On Earth, our magnetic field deflects most of it, creating auroras near the poles. These shimmering curtains of light are the result of solar particles meeting Earth's atmosphere, transforming invisible energy into peaceful displays of color. On planets without strong magnetic fields, the solar wind can slowly erode atmospheres over time. The Sun follows a natural activity cycle lasting about 11 years. During periods of higher activity, sunspots appear more frequently on its surface. These dark patches are slightly cooler regions caused by intense magnetic fields. Sometimes, the Sun releases bursts of energy known as solar flares or coronal mass ejections. While powerful, these events are part of the Sun's normal rhythm, not signs of instability. Despite these occasional outbursts, the Sun is remarkably stable. It is considered a middle-aged star, roughly halfway through its expected lifespan. For billions of years to come, it will continue burning hydrogen calmly, providing steady energy to the solar system. This stability has allowed life on Earth to develop, evolve, and flourish. From a distance, the Sun might appear solitary, but it is deeply connected to everything around it. Its gravity governs planetary orbits, keeps asteroid belts in place, and shapes the long, looping paths of comets. Even the most distant objects in the solar system feel its pull, however faintly. Throughout human history, the Sun has held cultural, spiritual, and practical importance. Ancient civilizations tracked its movement to measure time, guide agriculture, and mark seasonal changes. Temples, monuments, and calendars around the world reflect humanity's long-standing relationship with this steady source of light. In many ways, the sun was our first teacher of rhythm and routine. In modern times, solar energy has become an important part of global technology and sustainable development. Solar power supports economies, reduces environmental impact, and connects astronomy with everyday life. From satellites to renewable energy grids, the sun continues to shape both natural systems and human innovation. The sun's light also allows us to study the universe beyond. By understanding our own star, scientists gain insight into how other stars form, evolve, and eventually fade. In this way, the sun serves as a quiet reference point, linking our local experience to the wider galaxy. As you rest, it can be comforting to remember that the sun will rise and set regardless of human concerns. Its dependable cycle brings warmth to oceans, drives weather patterns, and sustains ecosystems. Even while you sleep, its energy continues traveling outward, touching planets, moons, and drifting particles far beyond Earth. Take a slow breath and imagine that warmth, not as heat, but as reassurance. A steady glow, constant and patient, holding the solar system together in gentle balance. Now, with the sun quietly behind us, we drift outward just a little, arriving at the smallest and innermost planet in the solar system. Mercury moves swiftly, silently, and with remarkable patience, circling the sun in a rhythm unlike any other world. It is a place of extremes, yet its story unfolds slowly, making it perfect for calm reflection. Mercury is named after the Roman messenger god, known for speed, and the planet lives up to that name. It completes one orbit around the sun in just 88 Earth days, making it the fastest planet in the solar system. However, despite this quick journey around the sun, Mercury rotates very slowly on its axis. One full day on Mercury, from one sunrise to the next, lasts about 176 Earth days. This creates an unusual balance between motion and stillness. Because Mercury rotates so slowly, its surface experiences dramatic temperature changes. During the long daytime, temperatures can rise to around 430 degrees Celsius, hot enough to melt lead. At night, with no atmosphere to trap heat, temperatures can plunge to minus 180 degrees Celsius. These extremes make Mercury one of the most thermally contrasting places known in planetary science. Mercury has almost no atmosphere. Only a thin exosphere made of atoms blasted off its surface by solar radiation and micrometeorite impacts. This lack of atmosphere means there is no weather, no clouds, and no wind. The planet's surface remains largely unchanged for millions of years, preserving ancient scars from impacts long past. The surface of Mercury is covered in craters resembling the moon in many ways. These craters tell a story of the early solar system when collisions were more common. Some of the largest impact basins on Mercury are hundreds of kilometers wide, formed by asteroids that struck with immense force. Over time, volcanic activity smoothed parts of the surface, filling lowlands with lava and creating vast plains. One of Mercury's most fascinating features is its enormous iron-rich core. Scientists believe the core makes up about 85% of the planet's radius. This dense interior gives Mercury a surprisingly strong magnetic field, especially considering its small size and slow rotation. This magnetic field interacts with the solar wind, creating a miniature magnetosphere around the planet. Mercury's proximity to the Sun means it is constantly bathed in intense sunlight. Yet, paradoxically, some regions of Mercury never see the Sun at all. Near the planet's poles are deep craters whose floors remain permanently shadowed. Temperatures there stay cold enough for water ice to exist. Space missions have confirmed the presence of ice in these shadowed regions, likely delivered by comets over billions of years. This discovery changed how scientists think about water in the inner solar system. Even in a place so close to the Sun, the right conditions can preserve ice if sunlight never reaches it. Mercury quietly teaches us that the universe often holds balance in unexpected places. From Earth, Mercury is difficult to observe. It never strays far from the Sun in our sky, appearing briefly at dawn or dusk. Ancient astronomers sometimes thought it was two separate objects, one seen in the morning and one in the evening. Over time, careful observation revealed its true nature as a single, wandering world. Modern exploration of Mercury began with the Mariner 10 spacecraft in the 1970s, followed decades later by NASA's Messenger mission. These spacecraft mapped the planet's surface, studied its composition, and revealed its geological history in remarkable detail. More recently, international missions have continued to expand our understanding, showing that even the quietest planets can offer profound insights. Mercury's landscape is marked by long cliffs known as lobate scarps. These formed as the planet cooled and contracted over time, causing its crust to wrinkle and fold. In this way, Mercury records its own slow aging process, a planetary memory etched into stone. Although Mercury has no moons, no rings, and no atmosphere to speak of, it remains deeply connected to the rest of the solar system. Its orbit helped early scientists test theories of gravity, including Einstein's general relativity. When Mercury's unusual orbital precession could not be fully explained by classical physics alone. As you rest, imagine standing on Mercury's surface during the long twilight near its poles. The Sun hovers low on the horizon, barely moving. Shadows stretch endlessly across cratered ground. There is no sound, no wind, only stillness shaped by gravity and time. Mercury reminds us that closeness to energy does not always mean abundance. Sometimes it means simplicity. A world stripped down to its essentials, quietly circling the Sun, keeping its secrets in silence. Now we drift gently outward from Mercury, gliding into the orbit of a planet that has fascinated humanity for thousands of years. Venus shines brightly in Earth's sky, often called the morning star or the evening star, appearing just before sunrise or just after sunset. Its beauty is calm and steady, yet beneath that soft glow lies one of the most extreme environments in the entire solar system. Venus is similar to Earth in size, mass, and overall composition, which is why it is often called Earth's sister planet. Yet, despite these similarities, Venus evolved in a dramatically different direction. Understanding Venus helps scientists better understand not only our solar system, but also the delicate balance that allows planets to remain habitable. Venus orbits the Sun at an average distance of about 108 million kilometers and completes one full orbit in 225 Earth days. However, like Mercury, Venus rotates very slowly. One full rotation on Venus takes about 243 Earth days, making its day longer than its year. Even more unusual, Venus rotates in the opposite direction of most planets, meaning the Sun would appear to rise in the west and set in the east if you could stand on its surface. This slow, backward rotation contributes to Venus's unique climate, but the planet's defining feature is its atmosphere. Venus is wrapped in an incredibly thick blanket of clouds made mostly of carbon dioxide, with clouds of sulfuric acid droplets. This dense atmosphere creates an extreme greenhouse effect, trapping heat with remarkable efficiency. As a result, Venus is the hottest planet in the solar system. Even hotter than Mercury, despite being farther from the Sun. Surface temperatures on Venus average around 465 degrees Celsius, hot enough to melt lead. This temperature remains nearly constant across the planet, day and night, pole to equator, because the thick atmosphere distributes heat evenly. The pressure at Venus's surface is equally intense. It is about 90 times greater than Earth's atmospheric pressure, comparable to being nearly a kilometer underwater on Earth. Any spacecraft sent to Venus must be built to withstand crushing pressure, corrosive chemistry, and extreme heat, making exploration a significant technological challenge. Despite these harsh conditions, Venus's surface is surprisingly young in geological terms. Radar mapping from orbiting spacecraft has revealed vast plains formed by ancient lava flows, towering volcanoes, and large, circular features called coronae, which are thought to form when hot material rises from deep within the planet and pushes up the crust. Venus may be the most volcanically active planet in the solar system today. While direct observations of eruptions are difficult due to the thick clouds, evidence suggests that volcanic activity may still be ongoing. Thermal hotspots and changes in atmospheric chemistry hint at a planet that is not geologically dormant, but quietly alive beneath its clouded skies. There are more volcanoes on Venus than on any other planet. Some estimates suggest there are hundreds of thousands of volcanic features scattered across its surface. Among them is Manat Mons, one of the largest volcanoes on Venus, rising several kilometers above the surrounding plains. These immense structures shape the planet's surface and contribute gases to its atmosphere. Venus has no moons and no ring system, adding to its sense of isolation. Its magnetic field is extremely weak, likely because its slow rotation prevents the kind of internal dynamo that generates Earth's strong magnetic field. Without a protective magnetic shield, Venus's atmosphere interacts directly with the solar wind, slowly losing lighter elements into space. Scientists believe Venus may not have always been so hostile. Early in its history, Venus may have had oceans of liquid water, much like Earth. Over time, increasing solar radiation and a runaway greenhouse effect caused water to evaporate. Water vapor, itself a greenhouse gas, trapped even more heat, accelerating the warming process until the oceans were lost entirely. This transformation makes Venus a powerful case study in planetary climate. It shows how small differences in distance from the Sun, atmospheric composition, and feedback mechanisms can lead to radically different outcomes. For scientists studying climate systems, both on Earth and on distant exoplanets, Venus serves as a cautionary example. From Earth, Venus has been observed since ancient times, It played an important role in early astronomy, navigation, and mythology. Civilizations across the world associated Venus with gods and goddesses of love, beauty, and war, inspired by its brilliant appearance in the sky. Despite its harsh reality, Venus continues to inspire wonder. Spacecraft exploration of Venus began in the mid-20th century, with both flyby missions and landers. The Soviet Venera missions were the first to successfully land on Venus and transmit data back to Earth. These landers survived only minutes, 2 hours. Yet, they provided invaluable information about the planet's surface, conditions, and composition. More recently, orbiters have used radar to peer through the clouds and map Venus in extraordinary detail. These maps reveal a world shaped by volcanic forces with fewer impact craters than expected, suggesting that much of the surface was resurfaced relatively recently in geological terms. As you imagine Venus, now picture a sky glowing softly orange beneath layers of thick cloud. The sun appears as a blurred, diffuse light, never sharp, never clear. The air is heavy, unmoving, pressing down in silent weight. Time passes slowly here, measured not by days and nights, but by deep planetary cycles. Venus reminds us that appearances can be deceiving. A planet that shines so brightly in our sky hides a story of extreme transformation beneath its clouds. It is a world shaped by imbalance, yet it holds essential lessons about atmospheres, energy, and planetary evolution. Now we drift gently into the orbit of a world that feels familiar, yet remains extraordinary when seen from afar. Earth, our home planet, floats through space as a delicate balance of rock, water, air, and energy. From a distance, Earth appears calm and luminous, wrapped in swirling white clouds and deep blue oceans, a rare combination in the known universe. Earth orbits the Sun at an average distance of about 150 million kilometers, a position often called the habitable zone. Here, temperatures allow liquid water to exist on the surface, a crucial ingredient for life as we know it. This precise placement is one of many factors that make Earth uniquely suited for complex ecosystems, stable climates, and long-term biological evolution. One complete orbit around the Sun takes Earth about 365.25 days. This extra quarter day is why we add a leap day every 4 years, a gentle adjustment that keeps our calendar aligned with the planet's steady journey. Earth rotates once every 24 hours, creating the familiar rhythm of day and night that has shaped human culture, biology, and sleep cycles for millennia. Earth's axis is tilted by about 23.5 degrees, and this tilt is responsible for the changing seasons. As Earth travels around the Sun, different hemispheres receive varying amounts of sunlight throughout the year. This slow, predictable shift gives rise to spring, summer, autumn, and winter, influencing agriculture, weather patterns, tourism, and the natural rhythms of life. Unlike Venus or Mars, Earth has vast oceans that cover about 71% of its surface. These oceans act as thermal regulators, absorbing heat during warmer periods and releasing it during cooler times. Ocean currents distribute warmth around the globe, shaping climates and making coastal regions more temperate. This quiet circulation plays a central role in Earth's long-term climate stability. Earth's atmosphere is another defining feature. Composed primarily of nitrogen and oxygen, it also contains trace amounts of carbon dioxide, water vapor, and other gases. This balanced mixture allows for breathable air, protects the surface from harmful solar radiation, and maintains a moderate greenhouse effect that keeps the planet warm without overheating. High above the surface, Earth's magnetic field stretches outward into space, forming a protective bubble known as the magnetosphere. Generated by the movement of molten iron in the planet's outer core, this magnetic field deflects charged particles from the solar wind. Without it, Earth's atmosphere could slowly be stripped away, as happened on Mars. Earth is the only known planet to support life, from microscopic bacteria to complex multicellular organisms. Life here emerged relatively early in the planet's history, more than 3.5 billion years ago. Over time, evolution shaped an astonishing diversity of forms, adapting to environments ranging from deep ocean trenches to high mountain peaks. The planet's surface is divided into continents and ocean basins, constantly reshaped by plate tectonics. Massive slabs of Earth's crust slowly move atop the semi-molten mantle beneath them. Where plates collide, mountains rise. Where they pull apart, new crust forms. This steady movement recycles nutrients, regulates atmospheric gases, and supports long-term habitability. Earth's moon plays a quiet yet powerful role in shaping life, formed likely from a massive collision early in Earth's history. The moon stabilizes Earth's axial tilt, helping keep seasons relatively predictable. It also drives ocean tides, influencing marine ecosystems and possibly even the evolution of early life forms. From space, Earth appears serene, but it is a dynamic and ever-changing world. Weather systems swirl across the surface, driven by solar energy and Earth's rotation. Winds, storms, and rainfall shape landscapes and sustain ecosystems. Over long periods, glaciers advance and retreat, deserts expand and contract, and forests shift with changing climates. Human civilization emerged only very recently in Earth's long history. In just a few thousand years, humans transformed landscapes, developed technology, built cities, and began exploring space. From this broader perspective, Earth's story is not just one of nature, but also of culture, economy, education, and global interconnectedness. Satellites orbit Earth in carefully calculated paths, supporting communication, navigation, weather forecasting, and scientific research. These technologies rely on precise knowledge of Earth's shape, gravity, and atmospheric behavior. Even as we reach outward into space, our understanding of Earth remains central to modern life. Seen from the darkness beyond the moon, Earth appears as a pale blue dot, fragile and luminous against the vast blackness. This view, captured by spacecraft, reminds us that Earth is not separate from the cosmos, but a small part of it, sustained by delicate balances and long-term stability. As we rest with this image, imagine Earth slowly rotating below, city lights glowing softly on the night side, clouds drifting peacefully over oceans and continents. It is a world of motion and stillness, complexity and calm, all at once. With Earth now gently behind us, our journey continues outward into the colder reaches of the solar system. Ahead lies Mars, a planet of rust-colored deserts, ancient rivers, and unanswered questions. We now drift gently away from Earth, letting its blue glow fade into the distance and turn our attention toward a quieter, rust-colored neighbor. Mars moves around the Sun at a greater distance than Earth, following a slower, more distant path. Often called the Red Planet, Mars owes its color to iron-rich dust that coats its surface, giving it a soft, muted glow even when seen through a telescope. A year on Mars lasts about 687 Earth days, nearly twice as long as a year on our home world. Yet, a single Martian day, known as a sol, is remarkably similar to Earth's day, lasting just over 24.5 hours. This familiar rhythm has made Mars an especially intriguing target for exploration and long-term human presence. Mars is smaller than Earth, with about half the diameter and roughly 1/10 the mass. This lower gravity has shaped the planet's atmosphere and surface over billions of years. Today, Mars has a thin atmosphere composed mostly of carbon dioxide, with traces of nitrogen and argon. The air pressure is less than 1% of Earth's, making liquid water unstable on the surface under current conditions. Evidence gathered by orbiters and rovers shows that ancient Mars once had flowing rivers, standing lakes, and possibly even shallow seas. Channels carved into the landscape and minerals formed in water tell a quiet story of a warmer, wetter past billions of years ago. One of the most striking features on Mars is Olympus Mons, the largest volcano in the solar system. Rising about 22 kilometers above the surrounding plains, it is nearly 3 times the height of Mount Everest. Olympus Mons formed over millions of years as lava slowly accumulated, unrestrained by plate tectonics, which no longer operate on Mars. Nearby lies Valles Marineris, a vast canyon system stretching over 4,000 kilometers, roughly the length of the continental United States. In places, the canyon plunges up to 7 kilometers deep. Its immense scale suggests powerful geological forces likely linked to the planet's early volcanic activity and crustal stretching. Mars experiences seasons much like Earth due to a similar axial tilt of about 25 degrees. However, because Mars follows a more elliptical orbit, its seasons vary significantly in length and intensity. Southern summers are shorter but warmer, while northern summers are longer and cooler. These subtle variations shape weather patterns and the movement of dust across the planet. Dust storms are among Mars's most dramatic phenomena. Some storms remain local, while others can grow to envelop the entire planet for weeks or even months. Fine dust particles suspended in the thin atmosphere scatter sunlight, reducing surface temperatures and creating a muted reddish haze across the globe. At the planet's poles, Mars hosts ice caps made of both water ice and frozen carbon dioxide. These caps expand and contract with the seasons, creating layered deposits that record climate changes over long periods. Studying these layers helps scientists understand how Mars's environment evolved and why it became so different from Earth. Mars lacks a strong global magnetic field today, which likely contributed to the loss of much of its atmosphere. Without magnetic protection, solar wind particles slowly stripped away lighter gases over billions of years. This process transformed Mars from a potentially habitable world into the cold, dry planet we see now. Robotic explorers have traveled vast distances across Martian terrain. Rovers such as Spirit, Opportunity, Curiosity, and Perseverance have analyzed rocks, sampled soil, and searched for signs of ancient life. Their discoveries reveal a complex history shaped by water, volcanism, and gradual climate change. Mars also holds cultural significance on Earth. For centuries, it has inspired myths, literature, and scientific curiosity. Its changing brightness in the night sky and reddish hue captured the imagination of ancient civilizations. While modern exploration fuels dreams of future human missions and interplanetary travel. In recent decades, Mars has become central to discussions about space exploration, technology, and long-term survival beyond Earth. Its proximity and similarities make it a natural testing ground for life support systems, sustainable habitats, and new forms of planetary science education. As we linger above Mars, imagine its quiet plains stretching endlessly below, settling softly after a distant storm. Ancient riverbeds lying still beneath the thin sky. Mars is a world of memory, preserving the echoes of what once was and offering clues about planetary evolution across the solar system. Leaving Mars behind, we continue our slow outward journey. Ahead lies the vast space between worlds, leading us toward the giant planets, where gravity, storms, and rings tell entirely different stories. As we drift farther from the sun, the light becomes softer and more distant, and the warmth fades into a gentle, cosmic cool. Ahead of us rises a presence so large and commanding that it feels less like a planet and more like a world unto itself. This is Jupiter, the largest planet in our solar system, a giant woven from clouds, storms, and immense gravity. Jupiter is more massive than all the other planets combined. If every planet were gathered together into a single place, Jupiter would still outweigh them. Its gravity shapes the solar system in subtle but important ways, acting as a kind of cosmic guardian that influences the paths of asteroids and comets. Some scientists believe Jupiter's gravitational pull may have helped protect the inner planets, including Earth, from excessive impacts over billions of years. A day on Jupiter is remarkably short. Despite its enormous size, Jupiter completes one rotation in just under 10 hours. This rapid spin causes the planet to bulge at the equator and flatten slightly at the poles. It also drives powerful winds that race around the planet at hundreds of kilometers per hour, creating bands of clouds that stretch endlessly around its circumference. These cloud bands are among Jupiter's most recognizable features. Light-colored zones and darker belts alternate across the planet's atmosphere, each representing regions of rising and sinking gases. Ammonia crystals form pale clouds, while deeper layers contain water, vapor, and other compounds. Together, they create a layered atmosphere of extraordinary depth and complexity. Within this shifting tapestry lies Jupiter's most famous feature, the Great Red Spot. This vast storm has been observed for more than 300 years and is large enough to swallow Earth whole. It rotates counterclockwise, powered by the planet's internal heat rather than sunlight. Though it has slowly changed shape and size over time, it remains one of the most enduring storms ever known. Jupiter has no solid surface in the way Earth does. As you descend through its atmosphere, gases gradually become denser, transitioning into liquid states under immense pressure. Deep within, Jupiter is believed to have a core made of heavier elements, possibly surrounded by a layer of metallic hydrogen. In this strange form, hydrogen behaves like an electrical conductor, generating Jupiter's powerful magnetic field. That magnetic field is the strongest of any planet in the solar system. It extends millions of kilometers into space, creating a vast magnetosphere that traps charged particles and produces intense radiation belts. These conditions make the region around Jupiter hostile to spacecraft, yet incredibly valuable for scientific study. Jupiter's internal heat plays a crucial role in its behavior. The planet emits more energy than it receives from the Sun, leftover warmth from its formation over 4 billion years ago. This internal energy drives atmospheric motion, fueling storms and maintaining the planet's dynamic appearance. Orbiting Jupiter is a family of moons unlike any other. With more than 90 known moons, Jupiter resembles a miniature solar system. Among them are the 4 large Galilean moons: Io, Europa, Ganymede, and Callisto, each offering a distinct and fascinating environment. Io is the most volcanically active body in the solar system. Its surface is constantly reshaped by eruptions driven by tidal heating, a result of gravitational interactions with Jupiter and neighboring moons. Lava flows, sulfur deposits, and towering plumes make Io a world of constant change. Europa presents a very different scene. Beneath its smooth, icy crust lies a global ocean of liquid water, kept warm by tidal forces. This hidden ocean makes Europa one of the most promising places to search for life beyond Earth. Cracks and ridges on its surface hint at slow movement and possible exchange between the ocean below and the ice above. Ganymede, the largest moon in the solar system, is even bigger than the planet Mercury. It has its own magnetic field, a rare feature among moons, and a complex internal structure that may include layered oceans beneath its icy shell. Callisto, heavily cratered and ancient, preserves a record of early solar system history, largely untouched by geological activity. Jupiter's influence extends far beyond its moons. Its gravity shapes the asteroid belt, creating gaps known as Kirkwood gaps, where orbital resonances clear material away. It also captures comets, sometimes temporarily, altering their paths and occasionally sending them inward toward the Sun. Throughout human history, Jupiter has been a source of fascination. Ancient astronomers tracked its movement across the sky, naming it after the king of the Roman gods. Its bright presence and slow motion against the stars made it a symbol of power and authority in many cultures. In modern times, spacecraft such as Galileo and Juno have revealed Jupiter's hidden depths. Juno's close passes over the planet's poles, uncovered massive cyclones arranged in geometric patterns, unlike anything seen on Earth. These discoveries remind us that even familiar planets can hold surprising secrets. As we hover quietly near Jupiter, imagine the endless layers of cloud drifting beneath us, storms forming and fading in slow motion, moons tracing graceful paths through space. Jupiter is not a place to stand, but a place to witness. a reminder of the immense scale and energy that shape our solar system. With Jupiter slowly turning below, we prepare to continue our outward journey toward ringed worlds and distant horizons, carrying with us the calm sense of wonder that only the cosmos can provide. As we continue our gentle voyage outward, the sun now appears smaller, its warmth more symbolic than physical. Ahead, suspended in the darkness like a slow-moving work of art, is Saturn. Even from a great distance, it is unmistakable. Its rings catch what little light reaches them, forming a pale halo that seems to float effortlessly in space. Saturn is the second largest planet in the solar system, though it is far less dense than Jupiter. In fact, Saturn is so light for its size that, in theory, it could float in a vast enough ocean. Like Jupiter, Saturn is a gas giant, composed mostly of hydrogen and helium, with no solid surface beneath its thick atmosphere. A day on Saturn is short, lasting just over 10 hours. This rapid rotation flattens the planet at the poles and stretches it at the equator, giving Saturn a noticeably squashed appearance. Despite its size, Saturn spins quietly, with winds that move swiftly but appear softer and more uniform than Jupiter's dramatic bands. Saturn's atmosphere is layered with clouds made of ammonia, ammonium hydrosulfide, and water vapor. These layers create subtle bands of color ranging from pale gold to soft beige. Occasionally, massive storms emerge, spreading around the planet like ripples across a pond, then slowly fading back into the background. The most iconic feature of Saturn is, of course, its rings. Composed of countless particles of ice and rock, the rings range in size from tiny grains to chunks as large as buildings. Though they appear solid from afar, the rings are vast, delicate systems with enormous gaps and divisions shaped by gravity. The rings are remarkably thin compared to their width. Though they stretch hundreds, thousands of kilometers outward, most are only tens of meters thick. This extreme flatness gives them an almost unreal quality, as if they were drawn rather than formed by natural processes. Scientists believe Saturn's rings may be relatively young, perhaps only a few 100 million years old. They may have formed from the remnants of a moon or a comet that wandered too close and was torn apart by Saturn's gravity. Over time, ring particles slowly fall inward or drift outward, suggesting the rings are temporary features on a cosmic timescale. Saturn is surrounded by an extraordinary collection of moons, each with its own character. Titan, the largest, is especially remarkable. It is the only moon in the solar system with a thick atmosphere composed primarily of nitrogen, with clouds of methane and ethane. On Titan, rivers and lakes exist, not of water, but of liquid hydrocarbons. Methane rain falls from the sky, carving channels and filling vast polar seas. Beneath its icy crust, Titan may also harbor a subsurface ocean of water, making it another intriguing candidate in the search for life. Another moon, Enceladus, appears small and quiet at first glance, but it hides remarkable activity beneath its icy surface. Jets of water, vapor, and ice particles erupt from cracks near its south pole, feeding Saturn's E-ring. These plumes suggest a warm ocean beneath the ice, rich in organic compounds. Saturn's magnetic field is gentler than Jupiter's, but still powerful. It extends far into space, interacting with the solar wind and creating auroras near the planet's poles. These auroras glow softly in ultraviolet and infrared light, invisible to human eyes, but beautiful in scientific images. Historically, Saturn has been observed since ancient times, moving slowly across the sky. Its rings, however, remained hidden until the invention of the telescope. When Galileo first observed Saturn, he was puzzled by its shape, seeing what appeared to be two small companions on either side. Later, astronomers revealed the true nature of the rings, transforming Saturn into a symbol of elegance and mystery. Even today, Saturn's appearance evokes calm and curiosity, standing apart from the more turbulent gas giants. Space missions, such as Cassini, deepened our understanding of Saturn and its moons. Over more than a decade, Cassini mapped the rings, studied the atmosphere, and flew repeatedly past moons like Titan and Enceladus. Its final dive into Saturn's atmosphere marked the end of one of the most successful planetary missions in history. As we linger near Saturn, imagine the rings stretching silently around the planet, each particle following its own orbit, yet together forming a harmonious whole. Time moves slowly here. Orbits repeat. Light glides across ice and shadow. Saturn reminds us that beauty does not need urgency, that complexity can exist without chaos, that some of the universe's most breathtaking sights unfold quietly, far from noise or haste. Leaving Saturn behind, we continue our calm journey outward, toward the distant ice giants, where the sun is little more than a bright star and the solar system begins to thin into interstellar space. As Saturn's rings fade softly into the darkness behind us, the solar system grows quieter and more spacious. The sun now appears as a small, steady light rather than a dominant presence. Ahead lie the iced giants, Uranus and Neptune, worlds shaped by cold, distance, and slow, graceful motion. Uranus is the first of these distant planets, orbiting the Sun at an average distance of nearly 3 billion kilometers. It takes Uranus about 84 Earth years to complete a single orbit, meaning one Uranian year spans almost a human lifetime. This long journey creates seasons that last for decades, unfolding slowly and gently. Its axis is tilted by about 98 degrees, likely the result of a massive collision early in its history. As a result, each pole points toward the Sun for long stretches of time, while the other remains in darkness. This unusual orientation gives Uranus the most extreme seasonal variations in the solar system. The planet's atmosphere is composed mainly of hydrogen and helium, with a significant amount of methane. Methane absorbs red light and reflects blue and green wavelengths, giving Uranus its soft blue-green color. The atmosphere appears calm and uniform at first glance, though closer study reveals subtle cloud patterns and gentle winds. Temperatures on Uranus are among the coldest recorded in the solar system, dropping to around -224 degrees Celsius. Unlike other giant planets, Uranus emits very little internal heat. This lack of internal warmth contributes to its relatively subdued atmospheric activity, creating a world that feels still and distant. Uranus is surrounded by a faint ring system, far less dramatic than Saturn's, but fascinating in its own quiet way. These narrow rings are dark and composed of larger particles, possibly remnants of moons that were broken apart by gravity. The planet also hosts a collection of moons, many named after characters from literature rather than mythology. Miranda, one of the most intriguing, displays a patchwork surface of cliffs, ridges, and valleys, suggesting a complex geological history shaped by internal movement and past collisions. Beyond Uranus lies Neptune, the outermost known planet in the solar system. Neptune orbits the Sun at a distance of about 4.5 billion kilometers and takes roughly 165 Earth years to complete one orbit. Discovered through mathematical prediction rather than direct observation, Neptune stands as a triumph of scientific reasoning. Neptune shares many similarities with Uranus in composition, but its personality is very different. Despite receiving less sunlight than any other planet, Neptune is remarkably active. It radiates more internal heat than Uranus, fueling powerful winds and dynamic weather systems. Neptune holds the record for the fastest winds in the solar system, with speeds exceeding 2,000 kilometers per hour. These winds whip through its atmosphere, forming dark storms and bright cloud bands that shift and evolve over time. The most famous of these, the Great Dark Spot, was observed by Voyager 2 before eventually fading away. Like Uranus, Neptune's blue color comes from methane in its atmosphere. But deeper atmospheric layers and internal heat give Neptune a richer, deeper hue. Its clouds cast long shadows, adding depth and texture to its distant skies. Neptune's largest moon, Triton, is especially unusual. Triton orbits in the opposite direction of Neptune's rotation, suggesting it was captured from the Kuiper belt rather than forming alongside the planet. Its surface is icy and reflective, with geysers that release nitrogen gas into the thin atmosphere. These geysers erupt slowly and quietly, driven by seasonal heating and internal processes. Dark plumes rise gently from the surface before falling back, creating streaks across the ice. Triton's activity reminds us that even in the coldest reaches of the solar system, change still occurs. Both Uranus and Neptune possess magnetic fields that are strangely offset and tilted relative to their centers. This creates complex magnetospheres that wobble as the planets rotate, interacting unpredictably with the solar wind. These magnetic environments add another layer of mystery to already enigmatic worlds. Historically, Uranus marked the first planet discovered with a telescope, expanding humanity's understanding of the solar system's size. Neptune's discovery later confirmed that unseen forces could be detected through careful observation and mathematics, reinforcing the power of quiet, patient inquiry. As we drift between Uranus and Neptune, the silence feels deeper. The sun's light is faint but steady, casting long shadows across icy clouds. Time moves differently here, measured in decades and centuries rather than days. These distant planets remind us that not all worlds announce themselves with brilliance or drama. Some exist quietly, holding their secrets close, shaped by cold, distance, and deep time. Ahead lies the edge of the planetary realm, where icy remnants and ancient debris mark the boundary between our solar system and the vast interstellar space beyond. As we move even farther from the warmth of the sun, the familiar structure of the solar system begins to soften and dissolve. The planets now feel widely spaced, and the darkness between them stretches longer and deeper. Here, at the edge of the planetary neighborhood, we enter a quieter realm, filled with icy remnants, ancient orbits, and gentle cosmic solitude. This is the domain of Pluto and the dwarf planets, worlds that move slowly and silently along distant paths. For many years, Pluto was known as the ninth planet, a small, mysterious point of light discovered in 1930. Though later reclassified as a dwarf planet, Pluto has lost none of its wonder. Pluto follows a long elliptical orbit that takes about 248 Earth years to complete. At times, it travels closer to the Sun than Neptune, while at other times it drifts far beyond into the deep cold. This elongated journey creates extreme seasons, with each season lasting decades. Despite its distance, Pluto is surprisingly complex. When the New Horizons spacecraft passed by in 2015, it revealed a world shaped by ice, time, and subtle activity. Vast plains of frozen nitrogen stretch across its surface, alongside mountains made not of rock, but of water, ice, as hard as stone, at such low temperatures. One of Pluto's most recognizable features is a large, heart-shaped region called Tombaugh Regio. This bright plain reflects more sunlight than surrounding areas and plays an important role in Pluto's climate. As ice sublimates and refreezes, it creates slow cycles that gently reshape the surface over long periods. Pluto has a thin atmosphere composed mainly of nitrogen, with traces of methane and carbon monoxide. This atmosphere expands when Pluto is closer to the Sun and collapses as it moves farther away, freezing back onto the surface like a soft, invisible snowfall. Orbiting Pluto is a family of moons, the largest of which is Charon. Charon is so large relative to Pluto that the two are sometimes described as a double system. They are tidally locked, always facing each other, moving together through space in a quiet gravitational dance. Beyond Pluto lies the Kuiper Belt, a vast region filled with icy objects left over from the solar system's formation. These bodies are ancient, unchanged witnesses to the earliest days of planetary creation. The Kuiper Belt extends far beyond Neptune, forming a wide, disk-like structure surrounding the solar system. Many dwarf planets reside here, including Eris, Haumea, and Makemake. Each follows its own slow orbit, shaped by gravity and time. Eris, slightly smaller than Pluto, but more massive, helped prompt the scientific reevaluation of what defines a planet. Haumea stands out for its elongated shape and rapid rotation, spinning once every 4 hours. It is also surrounded by a faint ring, a reminder that even small worlds can host complex systems. Makemake, cold and distant, reflects sunlight from its icy surface, remaining largely unchanged for billions of years. Occasionally, objects from the Kuiper Belt are nudged inward by gravitational interactions, becoming comets. These brief visits bring messages from the outer solar system into the inner realms. Even farther still lies the hypothetical Oort cloud, a vast spherical shell of icy debris extending, perhaps, halfway to the nearest stars. Though never directly observed, its existence is inferred from the paths of long-period comets. If it exists, as predicted, it marks the true outer boundary of the Sun's influence. This distant frontier is quiet, cold, and slow. Movement happens on timescales far beyond human experience. Orbits unfold over centuries. Changes occur over millions of years. Yet, nothing here is truly still. Gravity continues its gentle work, guiding every object along its path. The dwarf planets and icy regions remind us that importance is not measured by size alone. Even small, distant worlds can hold complex histories and subtle beauty. They are chapters in the solar system's story that speak softly, asking only patience and curiosity. As we drift through this outer darkness, the Sun is now just one bright star among many. The solar system feels less like a collection of destinations and more like a single, extended home, fading gradually into the wider galaxy. Ahead lies the boundary between the familiar and the unknown, where the Sun's influence weakens and interstellar space begins. Before we drift any farther into the quiet edges of space, let us gently turn back toward the center of it all. Even from the distant frontier, the Sun remains present, a steady point of light that holds the solar system together. It does not demand attention, yet everything moves because of it. The Sun is an average-sized star, calm by cosmic standards, but immense compared to anything we know on Earth. It contains more than 99% of the total mass of the solar system. Every planet, moon, asteroid, and comet traces its path in response to the Sun's gravity, like a slow, eternal dance. At its core, the Sun produces energy through nuclear fusion. Hydrogen atoms combine to form helium, releasing vast amounts of energy in the process. This energy takes thousands of years to travel from the core to the surface, moving gradually outward before finally escaping as light and heat. The sunlight that reaches Earth began its journey deep inside the Sun long before human civilization existed. By the time it touches your skin or lights the sky at dawn, it has already completed an epic, patient voyage through layers of plasma. The surface of the Sun, called the photosphere, glows at about 5,500 degrees Celsius. Darker regions, known as sunspots, occasionally appear. These spots are cooler than their surroundings and are linked to the Sun's magnetic activity. Though they look small from Earth, many sunspots are larger than our entire planet. Above the photosphere lies the chromosphere, and beyond that, the corona. The corona extends millions of kilometers into space and is surprisingly hotter than the surface below it. Scientists are still uncovering why this outer atmosphere reaches such extreme temperatures, a reminder that even our closest star holds mysteries. The Sun is not perfectly constant. It follows an approximately 11-year cycle of activity, during which sunspots, solar flares, and eruptions become more or less frequent. These events release energy and particles into space, occasionally interacting with Earth's magnetic field. When charged particles from the Sun reach Earth, they can create auroras near the poles. Curtains of green, purple, and red light ripple across the night sky, silent and slow, turning solar activity into natural art. These displays are gentle reminders of the sun's ongoing relationship with our planet. The solar wind, a continuous flow of charged particles, streams outward in all directions. It shapes the heliosphere, a vast bubble surrounding the solar system. This bubble shields us from much of the high-energy radiation that fills interstellar space, offering a kind of quiet protection. The Sun is about 4.6 billion years old and is roughly halfway through its life. For billions of years more, it will continue shining steadily, supporting life on Earth and maintaining the rhythm of days and seasons. Its future changes are slow, unfolding over timescales far beyond human lifetimes. Long before science understood fusion or gravity, the Sun was central to human culture. Ancient civilizations built monuments aligned with its movements, measured time by its cycles, and told stories to explain its rising and setting. Even today, daily life is shaped by daylight, warmth, and seasonal change. In modern times, the Sun supports more than just life and calendars. Solar energy has become an important source of renewable power, quietly transforming sunlight into electricity. This connection between star and technology reflects how deeply intertwined our future is with natural systems. As we think of the Sun now, imagine it not as a blazing force, but as a steady presence, a warm center, a reliable rhythm. It does not rush or hesitate, it simply shines. From the outermost edges to the innermost planets, everything feels the Sun's influence. Even in the cold darkness, its gravity and light remain. With this calm awareness, we are ready to continue outward once more, carrying the Sun's quiet steadiness with us as we explore the wider cosmic neighborhood. As we move once again away from the warmth of the Sun, the solar system gradually becomes quieter, darker, and colder. Beyond the orbits of the familiar planets lies a region that feels almost forgotten. A vast and gentle realm where time moves slowly. This is the Kuiper Belt. The Kuiper Belt begins just beyond Neptune's orbit and extends far outward into space. It is not a solid ring, but a wide, scattered disk filled with icy objects. These bodies are remnants from the early days of the solar system, preserved in the deep cold for billions of years. Many of the objects here are small, only a few kilometers across, composed of frozen water, methane, and ammonia. Others are much larger, large enough to be considered dwarf planets. Pluto is the most famous of these residents, but it is far from alone. Pluto's orbit is tilted and elongated, giving it a path unlike the 8 major planets. For part of its long journey, Pluto actually moves closer to the Sun than Neptune. Yet, even at its nearest, Pluto remains cold. Its surface temperatures far below anything experienced on Earth. Pluto and its largest moon, Charon, form a unique system. They orbit a shared center of gravity, making them more like a binary pair than a traditional planet and moon. Around them, smaller moons trace gentle paths, adding to the sense of quiet complexity. Other Kuiper Belt objects include Eris, Haumea, and Makemake. Eris is slightly smaller than Pluto, but more massive, and its discovery helped astronomers refine the definition of a planet. Haumea spins rapidly, giving it an elongated shape, while Makemake reflects sunlight with a bright, icy surface. These distant worlds change very slowly. A single orbit around the sun can take hundreds of years. Seasons last for decades. Surface changes unfold at a pace that feels almost frozen in time. The Kuiper Belt is also thought to be the source of many short-period comets. Occasionally, gravitational nudges send one of these icy bodies inward. As it approaches the sun, heat causes its surface to release gas and dust, creating the glowing tails that have fascinated observers for centuries. Comets are travelers between worlds. They carry material from the outer solar system into the inner regions, offering scientists valuable clues about the original ingredients that formed planets. In this way, the Kuiper Belt quietly contributes to our understanding of planetary origins. Spacecraft visits to this region are rare. In 2015, NASA's New Horizons spacecraft flew past Pluto, sending back detailed images and data. The encounter revealed mountains of ice, smooth plains, and hints of a thin atmosphere, reshaping our understanding of these distant objects. Later, New Horizons continued onward, passing another Kuiper Belt object called Arrokoth. This small, gently joined pair of lobes showed no signs of violent collisions, suggesting that some objects formed through slow, careful processes rather than chaos. The Kuiper Belt reminds us that the solar system does not end neatly at the last planet. Instead, it fades gradually into quieter territory, where ancient ice drifts in long, patient orbits. It is a place of memory, holding clues to how everything began. In the silence of this region, sunlight is faint. The sun appears as a bright star rather than a blazing disk. Shadows stretch long and deep. Motion is subtle, measured in centuries rather than hours. As we drift through this calm, icy ring, there is no urgency. Only the steady presence of time and the gentle pull of gravity guiding each object along its path. Beyond the Kuiper Belt lies an even more distant realm, one that stretches far into interstellar space. And that is where our journey will softly continue next. Far beyond the Kuiper Belt, past the last recognizable structures of planetary space, the solar system slowly dissolves into something quieter and more mysterious. This distant region is known as the Oort cloud, a vast and faint halo of icy objects that surrounds the solar system like a soft, invisible shell. The Oort cloud is so distant that it has never been directly observed. Its existence is inferred from the paths of long-period comets, those that appear suddenly from deep space, visit the inner solar system once, and then vanish for thousands or even millions of years. Their trajectories suggest a common origin far beyond the planets. Unlike the flat disk of the Kuiper Belt, the Oort cloud is believed to be spherical, extending in all directions. Some estimates place its outer edge nearly a quarter of the way to the nearest star. At such distances, the sun's gravity is gentle, and the influence of passing stars becomes significant. Objects in the Oort cloud are composed mostly of ice and dust, preserved in extreme cold. Temperatures here are only a few degrees above absolute zero. In this deep freeze, change is rare, and motion is slow beyond human comprehension. A single object in the Oort cloud may take millions of years to complete one orbit around the sun. Time itself feels different here. stretched and softened like a whisper that never quite fades. Occasionally, something disturbs this delicate balance: a nearby star passing through the galaxy, or the slow tidal pull of the Milky Way itself can nudge an object inward. When that happens, an icy body begins a long fall toward the sun, becoming a long-period comet. As it travels inward, frozen gases awaken. Sunlight warms the surface, causing jets of vapor to erupt, forming glowing comas and long tails that arc across the sky. For a brief moment, these ancient travelers become visible from Earth, reminders of the distant edges of our cosmic neighborhood. Many cultures throughout history have watched comets with wonder and curiosity. Once seen as omens, they are now understood as messengers from the solar system's earliest days. Their chemistry contains information about the original cloud of gas and dust that formed the sun and planets. Some scientists believe the Oort cloud formed early in the solar system's history, when giant planets scattered icy debris outward. These fragments were lifted into distant orbits by gravitational interactions, creating the enormous halo we infer today. The Oort cloud also marks the boundary between solar influence and interstellar space. Beyond it, the sun's gravity fades, and the galaxy begins to take over. Here, the solar system transitions from a family of planets into a single star among billions. If you could stand on an object in the Oort cloud, the sun would appear as a bright point of light, indistinguishable from other stars. There would be no familiar constellations, only a slow drift through a sea of starlight. This region teaches us humility. It reminds us that even something as vast as the solar system has edges. And beyond those edges lies a universe far larger than anything we can fully imagine. As we gently move beyond the Oort cloud, the solar system feels complete, its structure fading into the background of the galaxy. Yet our exploration continues inward again, toward the heart of astronomical discovery, the tools and human curiosity that allow us to understand these distant places. Our understanding of the solar system does not come from closeness alone. It comes from patience, from observation, and from tools designed to extend human senses far beyond their natural limits. Long before spacecraft, humans explored the planets and stars using only their eyes, tracking motions across the sky and noticing patterns that repeated with calm reliability. Early astronomers learned that some lights wandered against the background of fixed stars. These wandering lights became known as planets, a word that means to roam, even without knowing their true nature. People sensed that these objects held meaning and structure. The invention of the telescope gently transformed everything. When Galileo first turned his telescope toward Jupiter, he saw moons circling another planet, quietly proving that not everything revolved around Earth. This simple observation reshaped science, philosophy, and humanity's sense of place in the universe. Modern telescopes are far more powerful, yet their purpose remains the same: to gather faint light and allow it to tell a story. Space-based observatories avoid atmospheric distortion, capturing details that ground-based instruments cannot. Through them, we see swirling storms on Jupiter, seasonal changes on Mars, and the shifting colors of distant worlds. Radio telescopes listen rather than look. They detect invisible wavelengths, revealing magnetic fields, charged particles, and cosmic radiation. Through radio waves, scientists map planetary surfaces hidden beneath thick clouds, such as Venus, whose surface remains invisible to ordinary light. Beyond telescopes, robotic spacecraft have become our quiet ambassadors. They travel vast distances without sound, guided by mathematics and careful planning. Each probe carries instruments designed to measure temperature, gravity, chemistry, and motion with extraordinary precision. When a spacecraft approaches a planet, time slows. Commands take minutes or hours to arrive. Engineers wait calmly, trusting systems built years earlier. Success is often announced not by spectacle, but by a steady stream of data, arriving exactly as expected. Orbiters circle planets for years, watching slow changes unfold. They map surfaces, track weather patterns, and observe seasonal cycles. Through long observation, patterns emerge that would be invisible in brief visits. Landers and rovers bring exploration closer still. On Mars, robotic vehicles move slowly across dusty plains, studying rocks shaped by ancient water. Each movement is deliberate, each sample carefully chosen. These machines extend human curiosity to places no person has yet stood. Some missions focus not on landing, but on passing through. Flyby spacecraft gather rapid snapshots, capturing moons, rings, and atmospheres in fleeting encounters. Even these brief meetings provide invaluable insight into planetary systems. Gravity assists allow spacecraft to borrow energy from planets, bending their paths and increasing speed without extra fuel. This elegant technique reflects a deep understanding of motion and balance, using nature itself to explore nature. Exploration is not limited to large missions. Small satellites and CubeSats now perform focused tasks, testing new technologies and collecting targeted data. Their simplicity allows more frequent launches and creative experimentation. Human exploration remains part of the story as well. Astronauts aboard space stations observe Earth and space from orbit, conducting experiments that deepen understanding of life, materials, and physics beyond gravity's pull. These experiences shape future journeys deeper into the solar system. Throughout all exploration, one quality remains constant: patience. Space does not respond quickly. Signals travel at the speed of light, yet distances are so vast that delays are unavoidable. Planning spans decades. Results arrive slowly, often requiring years of careful analysis. This slow rhythm suits the nature of space itself. Planets move gradually. Orbits repeat over long time scales. Change happens quietly, almost imperceptibly. To understand the solar system, we must learn to match that pace. Every image returned from space is a form of storytelling. A shadow crossing a crater, a thin cloud drifting across a planet, a faint ring glowing against darkness. These details speak softly, asking to be noticed. As technology advances, future missions will listen more closely and see more clearly. Probes will explore icy moons where oceans may hide beneath frozen shells. Each mission adds another chapter to our shared understanding. Yet, even with all this knowledge, the solar system remains gentle and mysterious. Exploration does not diminish wonder. It deepens it. The more we learn, the more we realize how much remains unknown. As we prepare for the final part of this journey, the focus shifts inward again, toward reflection. What does it mean to belong to a solar system, to orbit a star, to exist in a universe both vast and calm? In the final moments, we will let the fact settle softly, allowing curiosity to fade into rest, just as planets fade into starlight. As our journey through the solar system gently comes to rest, it helps to slow even further and take a wider view. Beyond individual planets, beyond moons and rings and distant orbits, there is a simple truth that ties everything together. We are part of this system. Not visitors, not observers standing apart, but participants moving through space alongside every other object circling the sun. Earth is not separate from the solar system. It is one note within a long, balanced harmony. Our planet follows the same gravitational rules as Mars and Jupiter. It formed from the same ancient disk of dust and gas. The elements in our bodies were shaped by stellar processes long before the sun itself existed. When we look at the planets, we are quietly looking at variations of possibility. Each world shows a different outcome of temperature, distance, composition, and time. Some became rocky and dense. Others grew massive and gaseous. Some froze early, while others retained internal heat that still shapes them today. These differences help scientists understand not only distant planets, but Earth itself. By studying Venus, we learn about greenhouse effects taken to extremes. By studying Mars, we learn about water loss and planetary cooling. By studying Jupiter, we learn how massive planets protect inner worlds from excessive impacts. The solar system is also a record of time. Craters preserve ancient collisions. Layered rocks record volcanic cycles. Orbital resonances reveal interactions that unfolded over millions of years. Unlike life on Earth, which constantly renews itself, many planetary surfaces remain almost unchanged, holding memory without decay. Even the quieter regions tell stories. The asteroid belt marks a place where a planet never fully formed, shaped by Jupiter's gravity. The Kuiper belt preserves icy remnants from the solar system's earliest days. The Oort cloud, far beyond direct observation, likely surrounds everything like a distant shell of forgotten material. From this perspective, motion becomes comforting rather than overwhelming. Every planet knows its path. Every moon keeps time with its orbit. Chaos exists, but stability is far more common. The solar system has endured for billions of years, maintaining balance through subtle gravitational conversations. This sense of stability has practical meaning as well. Solar cycles influence space weather, affecting satellites, communication, and navigation systems that modern economies depend on. Understanding planetary motion helps guide spacecraft, protect technology, support global infrastructure quietly operating above Earth. There is also cultural meaning woven through planetary knowledge. For thousands of years, planets inspired stories, calendars, and navigation. They guided travelers, marked seasons, and shaped early science. Even today, their names echo mythology, connecting modern technology with ancient imagination. In moments of rest, thinking about the solar system can ease the mind. Problems feel smaller when placed beside planetary distances. Time feels softer when compared to orbital cycles. The steady movement of worlds reminds us that change does not have to be rushed to be meaningful. The sun will continue shining long after individual human lives pass. The planets will continue their paths without noticing. And yet, here and now, awareness connects us to all of it. Simply knowing these facts creates a quiet bond between thought and cosmos. As sleep approaches, it is comforting to imagine Earth moving gently through space, carried by gravity rather than effort. Night and day pass not because the world hurries, but because it turns calmly, exactly as it has for ages. Above, the planets trace their paths. Some rise before dawn, others glow faintly after sunset. All of them follow rules older than language, older than memory, older than life itself. You do not need to remember every fact. You do not need to picture every orbit. Let the knowledge settle where it wishes. Curiosity can fade into rest without disappearing. It remains waiting quietly, like a planet beyond the horizon. As this journey ends, allow the vastness to become gentle rather than distant. You are part of a system that moves with patience, balance, and remarkable calm. And with that thought, you can rest, knowing the universe continues its motion quietly while you sleep.